Okay. We'll start from current slide. Now, we talked about this last time, and I'm pretty sure most of the people that were here then are here now, but in case you weren't, and this is the first time you've heard it, when we were in our professional meetings Monday and Tuesday, Gabron is here. We found out there had been some pretty serious miscommunications. They have originally told us that the course covered 8.2, which is Introduction to Functions. Then later they told us, no, it didn't include 8.2. But some of the people that weren't there at that time, one of them was one who made out the final exam. So she included 8.2 in it. And about half the instructors are covering and half didn't know we were supposed to cover it. So we're at a kind of an impasse there because it's not in the syllabus, so we can't require you to be responsible for it. But it was in their syllabus, so they have to be responsible for it. So what we're going to do, the final exam does include 8.2 on it, but my solution, since we have so little time left, is to offer, well, the questions on 8.2 on the final will be bonus points, strictly. They will not count against you if you leave them blank or get them wrong, okay? If you get them right, you get bonus points for them, okay? It's going to be readjusting the way we calculate the final and stuff, but I can handle that. I know math, okay, so I think I can figure out that. Okay, now, the way to get you prepared to handle the bonus points, because we don't have enough time to do that, I did not allow for that, I'm proposing that the Monday of finals week, when we would normally have our final, rather than having a review session and doing a quick overview of 8.2 and anything else that you have questions about. And then, anytime after that review session is over with, which is about 10:30 that Monday morning, anytime after that morning, that afternoon, Tuesday, Wednesday, up to Thursday, you can take your final anytime that suits your schedule the best. Okay? How does that sound? Now, if any of you don't want the review period and you want to go and take the final Monday morning as it's scheduled, I'll get a proctor to do that, and you'll be able to. Now, if nobody wants a review session, then we'll all have the final on Monday morning. But I figured that some of you would want to have that. Okay. So, how does that sound? Okay. Yes? Okay. Well, how did it get turned upside down? How did that mess get in with this? Oh, I know. I think I know how it did. Okay. Module 13 quiz. Okay. I think it's quiz 4 you mean, right?
The one you gave out like 2 weeks ago?
Yeah, that was quiz 4, right?
4? Okay. Thank you.
We haven't done quiz 5 yet. Okay. In fact, it won't be, I don't think, a quiz 5. All right. Now, let's talk about a few other things as far as the course goes. I had hoped to have finished Module 13 by now, but we didn't quite get through. Hopefully we'll finish it today, which unfortunately means the Module 13 test will be Monday morning, okay? I hate to do that just 1 week before finals, but it's a little more than a week because we'll move the final back to Wednesday, which then means we only have one class, well, we have the rest of the day if we have time left over, and one class day to go over modules 14 and that section of 8.2. So that's a lot to do. So please be here next Wednesday because that's going to be a lot of, and then if you're here for a review session, we can continue that process. All right. Any questions? Therefore, the other thing that came up, if you haven't turned in that quiz, you have to have the quiz turned in before you can take your test on Module 13, or you have to ask me to give you a 0 on the quiz. I don't want to do that. So please get the quizzes done, preferably today or tomorrow. Now, let me go back to the finals week. Normally, I say you have all finals week to do that test if you're going to postpone it. This term we can't. This is the first fall term that we have started having graduations on campus in fall term. We used to only have one graduation a year, and that was in May. Now we're doing one for fall and one for spring, so therefore we're going to have it on the Birmingham campus, Birmingham West campus, and what that means is, and it's going to be on Friday rather than Saturday like it used to be. Well, what that means is Friday is no longer a final exam day, it's graduation day. So I can't be accepting, I won't be on this campus to administer an exam on Friday. So you have to get the exam done sometime after the review session on Monday, anytime up through Thursday. Now, are any of you graduating this term? Okay, that relieves some pressure, because if you're graduating, you have to have it done by Wednesday, because graduate grades have to be in by Wednesday, so you can graduate on Friday. Okay, so, all right. Any questions on any of that stuff? All right. If not, here's where we left off before. Any questions on math stuff also? Okay. This is on Module 13, page 22. The focus on writing a rational exponential expression as a radical expression. Goodness gracious, I can't talk today either. All right, do you remember what the rules were? Some of you weren't here, so you might need a refreshing from the others. How would you write this as a radical expression? This is exponential notation. We want to write it in radical notation. Anyone have an idea or clue? Help me out here. Anybody?
Should the 3x be in the radical?
Say again? You may have said right, I just can't hear.
Would the 3x be inside the radical?
Yes, 3x is what goes inside the radical. Perfect. Okay? So, let me get my pen set up. Okay? So the 3x will be inside the radical. Now I'm going to draw the radical, not necessarily through with the radical. Okay? Okay. Why is there a radical in this problem anyway? What clues you into that?
Multiplication.
Okay? A little more specifically, what is it about the exponent that tells you have to have a radical symbol? The denominator. If that was x squared, 3x in parentheses squared, you wouldn't need a radical symbol. It's that denominator means you have to have a radical. So guess what the index of this radical has to be? 3, that denominator. Perfect. Okay? So now we've accounted for that. What do we do with the 2? The numerator of that exponent. Second. Okay, what do we square? Okay. Now, I can't quite understand what you're saying, but I know it's right, okay? Because either answer is right. You can either put the 3x squared inside, the square inside the radical, or you could do the cube root of 3x and square it outside the radical. It doesn't matter, okay? Either one. Now, in this case, since there's nothing you can simplify this, I think it's better to do this form and go on and square what's inside there. And what is inside there? I'm going this one down to here. 9x squared. That's probably the best way to express this, because you get rid of the parentheses and the exponents and stuff like that. But this is a perfectly correct answer as well. And that's why things like WebAssign and that kind of stuff is only going to look for one correct answer. This is a correct answer, that's a correct answer, and this is a correct answer. I can't think of any others, but that would be all. And in the book, they did go all the way to the last one that I did. Okay, how about this one?
Just so I understand you, all three of those are correct answers.
All three of those are correct answers. Right. Okay. Second? I can't hear you.
Is that 2 over 3?
Yeah, it's negative 2x, and x is raised to the 2/3 power. What do you do with that? Anybody? Second? Exactly. That's not. Yeah, that's not part of the radical. Okay. Pablo is here. All right. Good observation there. Okay. Remember your rules of order of operation. You first deal with exponents. No, you deal with parentheses. That's why we did with that. The parentheses were there. This one doesn't have any parentheses. So then you go to please excuse. The excuse is exponents. The exponent, you deal with that first before you deal with the multiplication or negation. So the negative 2 is outside the radical. Very, very good observation. So negative 2, okay, and then what? The cube root of x squared. Another alternative way of writing that would be negative 2 times the cube root of x squared. But that's a little more awkward. There's extra parentheses and things like that. The most concise way is the first way, but both of those are correct. Okay? Make sense? In the book, they will go with the first way I did it. All right, any questions? Let's delete that if there are no questions, and let's just watch and see if they do it any differently. Okay, the first one, because the parentheses tells you do this thing to everything in there. The first, you do the cube root, because that's your denominator here, of what's in the parentheses, which is 3x, and then you square that. Or you could have done the cube root of 3x, the whole thing squared. This is a little simpler to do this way on this one, just because it simplifies to be this, the cube root of 9x squared. There's no way you can simplify that further. Are any of you at all tempted to do something with the 9? Good. Resist those temptations, okay? If that was a square root, by all means, you take the square root of 9. But the 9 doesn't have a cube root. 27 has a cube root, but 9 doesn't. X cubed has a cube root. X squared does not. So that's as simple as you can get it. Any questions? All right. Then this one, just as Bree said, the negative 2 is outside. It does not involve the radical at all. So that goes on the outside. And then they did it this way. It's perfectly fine. They brought the square into the x and left the 1/3 out there, which means only the x squared is what you take the cube root of. That's a rather awkward sentence, isn't it? Negative 2 times the cube root of x squared. Okay? You didn't have to do it in that order, but it's perfectly correct. Okay? You could have written that as negative 2 times the cube root of x, and that quantity, not the negative 2, but just that quantity squared. Either way would have worked. All right. If any of you are wondering why that works, let me just do it this way too. This doesn't necessarily make it maybe any clearer, but let me just show you. That's the same as the cube root of x times the cube root of x, isn't it? The cube root of x squared is x times x, so you could do it the cube root of x times the cube root of x. And if you did that, then you could do the cube root of x squared. So that's why either of those ways would work. This is just a little simpler to do. Okay, but both of those are equivalent. All right, there is a check your understanding 3. 2 more of those. I hope you can do those on your own. If you don't think you can, we could do one of those if you chose. Are you okay with it? Okay? All right. Let's move on to nothing. Okay. The next focus is not on the slide set. I mean, these are such huge slide sets, I can sort of understand why. No, they're not. Okay, Q is here. Does anyone else come in while I wasn't looking? Oh, yeah, I got you. All right. All right. This year's focus on writing a radical expression as an exponential expression. This is going the other way. All right. Rewrite the radical expression as an exponential expression. Here's the radical expression. The 7th root of x to the 5th. Anyone write that as an exponential expression? Say again? Said me? Yeah, okay. Who? A little louder. You don't need to do parentheses. You could if you wanted to, but you could just do x. Is that what you were saying? Perfect. It's x, what's inside the radical, and the exponent goes on top, the index goes on the bottom. Just exactly the reverse of what we were doing before, x to the 5/7. Does that make sense? The index of the radical is always the denominator of the exponent. The exponent of the either inside or outside the radical, that's what is on top. Okay? And if you'll notice in the book, that's exactly what they got. The second one they do here is the cube root of a cubed plus b cubed. Anyone tell me what to do with that one? Anybody? That is perfect. The a cubed plus b cubed in parentheses raised to the 1/3 power. All you can do. Now, if there was a parentheses out here with a 2 or a 7 or a 4 or something there, you could do. Thank you. Okay? The entire radicand, what's inside here, goes in parentheses with the rational exponent outside. And since here's what you can't do. You can't say, oh, you can pull out the cube. No, you can't. This is added. If that was multiplied there, yeah, that would be a cubed times b cubed. That would be a perfect cube. Take the cube root of that, and that would be ab. ab, multiplied. You can't do that to an addition. You can only root something that has been powered. Okay, remember we only said you can only divide things that are multiplied. You only can root things that are powered, not added. Okay, that you have a perfect power of it. So that's all you can do. Okay? You can't even split those up. So don't even try. Not with addition. You can with multiplication, but not with addition. All right. There is a check your understanding 4. 2 more of those. And then there's the objective 5.3B practice problems, 5 of those. Now the check your understandings are all located after the chapter in one place, and the practice problems are worked out in another place. I don't know why they don't put them together, but I guess they want you to play detective and find them. All right. Any questions? No more questions? Then we'll move on to
You want to have one If that was a minus sign.
What's that? If
that was subtraction.
yeah,
instead of
subtraction and addition, they treated the same. All you can do is.
Okay.
Yeah.
Sorry.
Yeah. Good question, though. Is it Jalen? Yeah. All right. And by the way, I should have said this earlier too. It's a real puzzle to me. We had several students who started the term, I thought, pretty well. You know, everybody did the first quiz, everybody did the first test, and generally the scores were quite good on both of those. But we've had a number of students who we have hardly seen since, well, first test, second quiz, sometime in there. They just quit coming. Now, if you know any of those students, please get in touch with them and let them know. I think the drop date for this term is Friday.
Last day of November.
What's that?
Very last day of November.
Yeah. So that's the last day they can withdraw from a class. A withdrawal does not hurt them academically at all. But if they don't withdraw, they're going to get a pretty lousy score. And that will hurt them academically. You know, then you have to make it up. And, you know, it hurts grade point average and that kind of stuff. And I was talking with another instructor, an adjunct instructor, and she was having trouble with people withdrawing too soon. I said, yeah, well, I've got some that just quit coming too soon and then don't withdraw. That's my, yeah. And I showed her some of the scores. She said, why did they quit coming? I said, I do not know. So anyway, if you know any of those students, please contact them and encourage them to go on and drop the course. It doesn't hurt them academically at all. They have to do it by Friday, though. I doubt if they're listening, or else I'd say, well, I'm going to put it on this, but obviously they're not listening. Okay, or I would think they're not. All right. Did I just go backwards? I think I did. I got to running my yap, okay? Yuck. That's not what I want. Now I have to start all over again. All right, 13.5C, the last section in Module 13. Why it didn't come up properly. And here's Saya. All right. Anyone else come in since I called roll? I haven't acknowledged your presence. Okay. Okay, here we go from current slide. So, Module 13, as it's been all module, is rational expressions and radicals. Rational exponents of radicals. I keep saying it wrong. Radical expressions. And that's what 13.5 is. Rational exponents and radical expressions, just like we were doing. And this objective is to simplify radical expressions that are roots of perfect powers. Okay? Nice mouthful of words, isn't it? All right. Now, if you recall, if you have the square root of a square, you just undo the square, right? It just produces 8. If you have the square root of 6 squared, that would be 6. Or you can square this, 36, the square root of 36 is 6. Now, I don't want to know what, oh, okay, here it is. A little review. Suppose a is equal to 6. Okay. Square root of a squared. Now, here's the problem. Square root of a squared, let's let a be negative 6. Square root of a squared would be square root of negative 6 squared. Well, negative 6 squared is 36. And you take the square root of 36, and you get 6. Well, that's not what you started with. You had started with a negative 6, so you can't always say that the square root of a squared is a, unless you know that a is positive. Okay. So whether a is positive or negative, the square root of a squared itself is always positive. You can never get back to a negative 6 with a square root. Another way to state always positive is to use the absolute value symbol. And that is the best way to express that. Without having to say the word always positive, you say absolute value of A. Now this is true when that's an even power and this is an even index. If this was an odd power, odd index, it doesn't matter. You can have a negative result from that. You can't with an even power and even index. Okay. I guess we're going to talk about that now. Okay. In general, the value of the nth root of a to the n depends on whether that n is odd or even. If it's odd, it's always this. You can just take it out. If it's even and you do this, you have to put the absolute values in. Okay? Now, if you had a negative in front of this, we'll just do this, absolute value, and then put the negative sign in front of that. So that doesn't influence how you do this. But if n is even, you have to put absolute value bars. If n is odd, don't. Because the a can't be negative or positive. It doesn't matter when you have an odd index and an odd exponent. Okay. Now, note that a variable expression is a perfect power if the exponents on the factors are evenly divisible by the index of the radical. Okay? Where did that note come from? I think I see. They gave, let's back up one. Okay. This is a phrase on the top of page 23 in section, in module 13. And then they left out a bunch of stuff. Okay. So let's do some of that bunch of stuff they left out. Okay.
Which section are we in now?
What's that?
Which section are we in?
We're in 13.5, but we're in the C part, objectives 13.5C.
Okay.
Okay.
Thank you.
All right. So here's for example, that they give and they didn't put on the slide set. Okay. So let's do some of these. If I can get my pen to come back. Come back, pen. Come here. Okay, here it comes. All right. What in the world would this be? The 6th root of y to the 6th. Anybody? Say again?
Would it be y with absolute value?
Absolutely. It would be y. I saw some mouths saying y, but you'd have to put absolute value bars. Why? Even index, even power. Have to do it. Okay? How about this one? A negative 12th root of x to the 12th. Okay, the negative hangs in there of what? Absolute value of x. Okay, now this does give you a negative answer. This doesn't, but this does because the negation does. And why is that? Remember, please excuse my dear Aunt Sally. I don't know what she did, but please excuse her because you do the exponentials. Thank you. First, which is this, before you do the subtraction, the negation. Okay? So you hang off on that until the end, and there you have it. So do what's over there first, then do the minus sign. So yeah, that's negative absolute value of x. No matter what sign x had to begin with, it's going to be a negative answer now. Okay? And how about this one? The 5th root of b to the 5th power. What's that? Okay, yes, it's b. All right. Why? The index and the exponent are odd. That can be positive, it can be negative, no sweat at all. Okay. Oh, not much sweat. Okay. Now, there are a few others before we get to the note. Okay. So let me erase these. Any questions before I erase them? See some people still writing. Everybody through? Okay. Erase these, and let's do a couple more. This is a take note, and then we'll get to the note. Let's simplify this. The fourth root of x to the fourth, y to the eighth. Ooh, man, what do we do with that? Say again? Okay. X times y squared. Is that all? Absolute values. Now the y squared, there's no problem there. Whether y is positive or negative, that's always going to be positive. Square any number, it's going to be positive. That x could be negative, so you have to put the absolute value bars. Okay? If that's what you had, y squared would be your answer, and you don't even have to put absolute value bars. But with the x in there, you do. So that could be positive or negative. Very good. Okay? Whoa! All right. I knew they were going to do this, I just didn't know when. The take note that I mentioned, but I didn't read to you. Because we stated that variables within radicals represent positive numbers, we will omit the absolute value symbols when writing an answer. So they've told us all this and got us drilled into it, and now they say, from now on, we're just going to assume all that the variables are positive, so we're going to leave them off. So that's why from now on, they're not going to put absolute value bars. So I guess that makes sense. So on this one, when I saw their answer, I said, not right, but no, I didn't read the take note. From now on, we'll always assume the variables are positive. Okay? If you don't know that's the case, you put absolute value bars. But if from now on, the book is telling you that's what the take note is, because we stated that variables within radicals represent positive numbers, we will omit the absolute value symbols when writing an answer.
Which one do you want on your test?
We're going to go with this, what they just said here. Okay? From now on, we're not going to worry about the absolute value bars. Okay? In real life, when you might have to worry about it, worry about it. But from now on, we're not going to worry about it here. Okay? Sort of like practicing for a fire drill, but saying we're not really going to do that today, you know. So, bad news. Okay. But from now on, we'll assume all the variables are positive. And if you know that in real life, then you don't have to worry about absolute value bars, because you're not going to get a negative. From now on, we'll say that. Assume all variables are positive. So, here's another one. The B here. Oh, that's an eraser. Okay. Pen. The cube root of 125 C ninth D sixth. Okay? What in the world do we do with this? Say again? Okay. Okay. I think what you're trying to say was right, but I thought I heard the word said wrong. 125 is a perfect what?
A perfect cube.
A perfect cube. I thought you said a perfect square. Okay, yeah, okay. It's a perfect cube of 5. Okay, so then that can come out as a 5. Next. Yes, that would be C to the third. And next, D to the second. Now, in this one, we wouldn't even worry about whether anything was positive or negative because it's a cube root. It can handle anything. Okay? So, yep, that's what we get. Now, I'm going to show you 2 ways that you can think of doing that. And I hope you'll remember that I showed you this with square roots. until someone saw there was an easier way to do it. You could do this as the cube root of, factor that. Smallest prime number will go into 125. 2 won't go into it. 3 won't go into it. 5 will go into it. What's left when you divide 5 into 125? Ooh, hard math. 25. And 5 will go into 25. 5 times 5. So, like you already noted, that's the perfect cube of that. And then you could do, you don't have to, I don't recommend it, C times 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 C. 1, 2, 3, 4, 5, 6, 7, 8, 9 C's, and D times D times D times D times D times D. 6 D's. I don't recommend doing it this way, folks. Because that's a cube, the index is a 3, group all of your things by 3's. That would give you a 5 on the outside. There's a C on the outside, but there's another C on the outside and another C on the outside. 3 of those would be C cubed, and then group this in 3's, and you have 2 groups there, D squared. Okay? Now, I really think it's a good idea to do that with the number part, the coefficient part. But let me show you the easier way to do it with the radical parts, what we were just doing. So let's split this into the cube root of 125. And we know that's 5. And then we'll do the cube root of C to the 9th. But guess what? You can write that in exponential notation, right? That would be C to the 9 over 3, wouldn't it? Okay? And then you have a D, write that in exponential notation, D to the 6 over 3, because whatever's out here is your denominator. Well, this will be 5. The cube root of 125 is 5, and 9 divided by 3, C cubed, D squared. Okay? Either one of those ways works. In fact, that's probably what you did when you got these. Okay? In your brain, you did that. So, it's another way of thinking of it. Writing it, at least the variable part, as a rational exponent, exponential form. Okay? Now, that's why they come up with, note that the variable expression is a perfect, note that a variable expression is a perfect power if the exponents and the factors are evenly divisible by the index of the radical. Okay. The chart below shows roots of perfect powers. Knowledge of those roots very helpful in simplifying radical expression. Now, this is what I suggest you do at the very beginning, didn't I? Write 1 through 10 or something like that, and then square it, and then cube it, and then fourth it, and then fifth it, as many as you want to go, and get these. So here's the square root. Square root of 1 is 1, square root of 4 is 2. You know those, right? All right. How about these? Square root of 36, 49, 64, 81, and 100. Good. How about cube roots? 1, 2, 3, 4, 5. I don't go any higher than that. I don't remember them anyway. This one? Okay. The fourth root of 1 is 1. The fourth root of 16 is 2. Fourth root of 81. 3. Fourth root of 256. I don't remember that, but yeah. 625. Here's what I do remember. For the fourth roots, if you square this number, 2 squared is 4, so the fourth root, I'm sorry, 4 squared is 16, so the fourth root of 16 is 2. 9 squared is 81, so the fourth root of 81 is 3. 16 squared, do I know that? It's 256, so its fourth root is 4. And 25 squared, I do know that really, is 625, And so its fourth root is 5. So I do that one. I don't even get this high here, okay? Fifth root of 1, I know that. And fifth root of 32, I know my 2's. 3's, I'd have to sit down and figure that, okay? I don't keep that one stored in the memory bank. And 6 roots, 1 and 2 maybe is all I would go on that. So you don't have to memorize all these things, but what you can do is factor. And then if you get a factor of 3 factors under the radical, pull it out, okay? So that's why I go back to that, because I don't memorize big numbers, okay, well at all. Have trouble with telephones, okay? Not really. I developed a method to try to remember those. All right, any questions so far? All right. Make sure they haven't skipped something else here. Okay, no, they don't. There's not anything. If a number is not a perfect power, its root can only be approximated. Examples are the square root of 5. That's not a perfect square. So you just make an approximation. Cube root of 3, we don't know what that is. That's why you have calculators, right? These numbers are called irrational numbers. It has nothing to do with gender, by the way. It's just irrational numbers. Nothing. There is no perfect root. If you try to write the decimal number, the decimal goes on and 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 never repeats a pattern. Any pattern whatsoever. Okay? Even if it looks like it might, after a while, it won't. Okay? The decimal representation never terminate, never repeat. That's what defines an irrational number. And there are tons of them out there. Second? I still can't hear, sorry. Fields, got it, rotation. Okay. Yeah. I'm sorry if I keep blinking a lot today. I've evidently gotten an infection in an eye and it really hurts like crazy. Okay, so that's about irrational numbers. And before we go to the focus, there is one other small example here. Simplify this. Okay? Again, it's hard for me to see. The fifth root of negative 243 x to the fifth y to the 15th. Okay? Now, because they just showed us this in a table, we can do this one without doing anything else. But I'm going to suppose we didn't. Now, the first thing that strikes me, almost a warning sign, is what? Here's a minus sign inside a radical. Is that allowed? If the index is odd, it's okay. If that was an even index or just the radical, which means square root, would not be okay. But with the odd root, that is okay. So the answer is going to be negative. Okay? So I'm going to pull out the minus sign. Okay? Now, fifth root. Okay? Now, again, I don't know this one. I don't keep this in my memory banks, but it's easy to see what it is. But let's start our factorization process. That's why I said the coefficients usually, unless you happen to know them, that's the way to go with it. Okay? What's the smallest prime number will go into 243? 3. Huh? Jackson? Kylie? Huh? Okay, Kylie. Got it. My hearing's so bad. Okay. I would start, okay, so 2 won't go into it, 3 will. 3 times what? 3 will go into 24. 3 will go into 24. Somebody help me. 8 times, and 3 will go into 3 1 time. So that'll be 81. Hey, 81 I know is 9 times 9, which is 3 by 3, that's 9, times 3 by 3, that's another 9. There it is, okay? Sure enough, that is a perfect fifth root, okay, fifth power, okay? And then the other part, and I'm going to shorten my radical here. I'm breaking this into the pieces now. This next piece, I'm not going to write, well, you could write it this way, the fifth root of x to the 5, okay? And the next part, I think I'm going to write that one as exponential notation, y to the 15 over 5, right? And I could have done that one 5 over 5, that would have worked too. So what is this? The minus sign's still there. Negative 3 x y cubed. Perfect, perfect, perfect. Way to go. Got it? Any questions on it? You don't have to do the rational exponent. To me, that's just the easier way to do it. Okay? So, let's now go to the focus as soon as people quit writing. Any questions on it so far? Is it making sense? Good deal. Okay? There's lots of ways to get there. You go with the way that you see and understand and say, oh yeah, okay, I got that one, okay? So you don't have to do it my way, the book's way. You do the way that's right as long as you take right steps, okay? Don't make up your own rules, okay? Not allowed. We make up the rules. You have to follow, okay? Any other questions? All right. Now let's go to the focus. All right. What do you think we're going to do here? Square root of 49x squared. 7x. Boy, that was easy, wasn't it? Square root of 49 is 7. Square root of x squared is x. How about the cube root of a negative 125A6B ninth? The negative's there. 5's there. A squared's there. B to the third is there. Perfect. Y'all are good at this. Okay? How about that minus outside? Is that okay? Sure. Just a minus. Okay. What's the fourth root of 16? Is there? Or is that an irrational number? Two. So minus 2. A. B to the second. Y'all are good. Y'all are mighty good. Okay? I should keep saying that when I'm grading your final swap. No, okay, no. Okay. All right, any questions on that? Break it up into the pieces. Do one piece at a time. You got it not. Now, if you didn't see that 125 is a perfect cube of 5, you can factor it out, and then you'll see that. Same thing with 16. 2 will go into 16, 8. 2 will go into 8, 4. 2 will go into 4. 2 times 2. That's 4 2s. 4 on the outside. Group those together. Okay? So there's lots of ways you can do this. Do the way that you understand, feel most confident in doing. Got it? All right. There is also a Check Your Understanding 5. It has an answer on page S5, supplement 5. And then there's 5 practice problems. Please do those. Especially the Check Your Understanding as soon as you can, the practice problems whenever you want to get to them. And that, folks, finishes, well, no, wait, sorry. Let's see how they did these. Can I erase? Yay or nay? Anyone still writing? Okay. All right. Let's see how they do it. The first one, they did just like we did. Square root of 49, 7, square root of x squared of x. 7x. Didn't show you anything else, okay? This one, the cube root, they just, again, they did just like you did. They just write it down, okay? Because this is an odd index, you can pull out the minus sign, okay? It's perfectly good to have it there. And then the cube root of 125 is 5. Cube root of a to the 6 is a squared. Cube root of b to the 9. Perfect. They're all perfect cubes. On this one, the minus sign's already out there, so it's not hurting a thing. But don't lose it. They gave it to you, so keep it. Okay? 4 through 16. If you go to your table, you'll see that's a 2. Or you could do 2 times 8 times 2 times 4 times 2 times 2. That's 4 2's. So that's the 4 pulls out a 2. A to the 4th, that would be a. B to the 8th. Okay. Now, what I'm really surprised they didn't do is show you some that have powers that aren't perfect powers of the root, if you know what I'm talking about. Then you just factor out those that are and leave the others inside the radical. We did it with squares, but they didn't do it with the bit higher roots. I'm not sure why. But evidently they're not going to ask you that on the test, I hope, anyway. Okay. Because all the practice problems are just like that. Okay. That's the last in Module 13. Oops. So, any questions on Module 13? We will be having the test on this. The rest of this stuff here is solutions to those various check yourselves, or whatever you call those things. Yeah, check your understandings, and then they do the practice problems. So all these are in here. They have pages of worked out solutions. So we're ready, aren't we, to move on to Module 14. And this is one long module, so there's no way we're going to get it all done, but let's do as much as we can. That's another reason it's going to be good to use that Monday to pick up some of these too. What we're talking about here are quadratic equations. What in the world does that mean? Anyone have a clue what we mean by a quadratic equation? Say again?
An equation with 4 terms.
Okay, no, not quite. That would be a 4-term equation. No. It sounds like it has something to do with 4s. It really doesn't. It has to do with 2s. Okay? Do not know where the name quadratic came from, but it only is powers of 2. So section 14.1 is solving quadratic equations by factoring or by taking square roots. You can use either method if you can. The first objective here is 14.1A, solve quadratic equations by factoring. B, I bet you, is going to be squaring. It'll take you square roots. Okay. An equation that can be written in the form, this form, ax squared plus bx plus c is equal to 0, as long as the a is not 0. See, those coefficients can be any number in the world, any real number, positive, negative, fraction, decimal, rational or irrational, fine. Okay, but a can't be 0. Now here's why it can't be 0. If a was 0, what kind of equation is that? Linear, not quadratic. So it can't be a quadratic equation if a is 0. You must have a coefficient for the x squared. Okay? B or C could be 0 or not, doesn't matter, but A cannot. So here are examples of quadratic equations. That. Here your A is 4, your B is -3, your C is 1. This is also a quadratic equation. Your A is 3, which is not 0. The B is 0, no sweat there, and the C is -4. Okay? Quadratic equation is also called a second-degree equation, or a second-degree polynomial equation, if you want to use a more specific term. A quadratic equation is in standard form when the polynomial, they use polynomial, is in descending order of the powers and it's at equals 0. That's standard form for a quadratic equation. The exponents are 2, 1, 0, and then the constant is a 0. Okay? All three of those, that one, this one, and this one, are all in standard form. Okay? Any questions? All right. Now, anyone remember what the principle of zero products is? If you have a product of any two entities, whatever two entities you have, and that product is equal to 0, guess what you know about one of those two entities? At least one of them has to be 0. They may both be 0, or at least one of them's got to be a 0. No other way you can multiply two entities together and get 0 unless one of those two entities is 0. Only way you get a 0 from multiplication. So here's how they write it. If A times B is 0, then either A is 0 or B is 0. It could be both of them, but one or the other has got to be. The principle of zero products can be used in solving quadratic equations. That's our, if the quadratic equation can be factored, then it's this is equal to 0, then one of those two will be 0. Okay? Let's see if they hit anything before this. Yes, they do. So let me back off. Now let me use this one here. We're not going to do this yet until we do, the others. All right. 2x squared minus x is equal to 1. Is that a quadratic equation? Say again? Was that a yes or a no? No. No, it was not. No. Yes, it is a quadratic equation, but it's not in standard form. Okay, so it is a quadratic equation, it's just not one in standard form. How can we make that in standard form? Subtract 1 from both sides of the equation. Okay, and that would give us 2x squared minus x minus 1 is equal to, and what do these add to? 0. Now it's a quadratic equation in standard form. Okay? And what do we hope beyond all hope that we can do to it? What's your F word? Factor it. Now, if we can factor it, what's the only possible factorization for 2x squared? 2x times? What would be the other factor? X. Perfect. Then we look at the sign of the last term. What does that tell us? Yeah, one of them's a plus and one of them's a minus. And they have to be 1s, okay? But we don't know if we got it right, do we? Not until we FOIL it and see. 2x times x is 2x squared. Yes. 2x times minus 1 is minus 2x plus x would be minus x minus 1. Yes. If you had put the minus here and the plus here, it follows all the rules, but it doesn't give you the right answer. So y'all either looked ahead, or you were really bright, or you guessed well. Okay. No, you were really bright. Okay. I knew that. Now what do we do? The zero product principle, and that tells us what? Okay, either 2x plus 1 is equal to 0, or x minus 1 is equal to 0. Well, what does that first one? Now that's a linear equation. We know how to do those, right? What do we do on the first one? Okay, what we're trying to do is isolate the x, so we subtract 1 from both sides, and that gives us 2x, that goes to 0, is equal to negative 1, and then do what? Divide by 2, and that gives us x is equal to negative 1/2. Oh, one of our favorite fractions, isn't it? Okay, on the other side, it's even easier. Add 1 to both sides, and that gives us x equal 1. Okay, now the perhaps anal retentive person that I am, I want to make sure I got it right. So I'm going to plug both of these answers back in here. Oh, what a pain in the neck that looks like, doesn't it? I plug a minus 1/2 into here. What's minus 1/2 squared? Nope, squared, not added. Minus 1/2 squared. Maybe you should plug them in. No, okay. Minus 1/2 squared is? Anybody? 1/2 times 1/2. 1/4. Minus times minus is plus. That'd be 2 times 1/4 is? 2 times 1/4 is? Yeah, 0.5. Okay, 1/2. Minus of minus 1/2 is? Okay, minus of minus is plus. So 1/2 plus 1/2 sure enough is 1. I hope that's what you were saying. Okay. All right. That one was hard because it was a fraction, but it does check. 1 is going to be really easy. 2 times, well, what's 1 squared? 2 times 1 is? Minus 1 is? Yeah. 2 minus 1 is? 1. Yes. Both of them work. If you can do fractions. Okay. If not, you just have to hope that you got it right. Okay. Now, I didn't say that, did I? All right. How about this one? X squared is equal to 10x minus 25. Is that a quadratic equation? But it's not in standard form. How do we get it in standard form? Subtract 10x from both sides and add 25 to both sides. This is getting ugly, isn't it? Okay. Okay, don't agree with that. Okay. This becomes x squared minus 10x plus 25 is equal to, that adds a 0, that adds a 0. Yes, we got it in standard form. Okay? Now, what would we try next? Factor it. Okay? Let's see if it'll factor. What's the only possible factorization of 25 of x squared? X times x. And then we look next at the sign of the last term, which is positive. That means these two have to be the same, but because the middle term's negative, they both have to be negative. Okay, now what is one possible factorization of 25? 5 times 5, and that looks like it'll do. And guess what? X times x is x squared, minus 5x is minus 10x, plus 25. Yes, that works. So what's our solution? X equals 5. It's either x minus 5 is equal to 0 or x minus 5 is equal to, you don't have to do this, I'm just showing you. Add 5 to both sides, and that gives you x is equal to 5 because that goes to 0. Add 5 to both sides, and that also gives you x is equal to 5. Now what we call that is a double root. Okay? Only one real root, but it's a double root. Okay? Multiplicity of 2, we would say. But it's only one number. Okay. Now, if you're beginning to wonder how that can be, this one has 2 answers, that has 1. Let me just show you something that this is, maybe later in this thing you'll do it. I'll tell you something. Every quadratic equation will graph as a thing. Anyone know what it's called? A parabola. Always. It may look like that. It may look like this. It may look like anything like that. If it crosses the x-axis twice, that gives you 2 solutions. If it comes up here and just touches the x-axis at one place, that gives you 1 solution. Guess what another option would be? Never crosses the x-axis. There are quadratic equations with no solutions. Okay. Now, a linear equation, unless the slope is 0, is always going to cross the x-axis somewhere. But a quadratic may be not crossing, only touch in one place, kisses the x-axis, or it crosses twice. Okay. Never any more than twice. So if you find 2 solutions for a quadratic, don't look any further. That's all she wrote. Okay, does that make sense? All right. They call it a double root. So now we're ready, and boy, do they ever jump into it with 2 feet. Here is our solved by factoring. Is that a quadratic equation? And do we love it? No, why not? It has fractions in it. Ooh, boo, hiss. But the good news is it's an equation. So guess how we solve equations that have fractions in the equation? Find the, what were we going to say? Least common denominator. And what's the least common denominator of all the denominators on both sides? And by the way, this is also in standard form, but it's still ugly because it has those denominators. So what's the least common denominator of all those denominators? 6. What do we do with it? Multiply everything on both sides by 6. Okay, so we'll multiply this by 6, we'll multiply this by 6, and we'll multiply this by 6, and we'll multiply this by 6. Okay, and let's see the magic that happens. 2 will go in the 6, 3z squared, 3 will go in the 6, 3 will go in the 6, twice, plus 2z, 6 will go in the 6, minus 1, and 0 times 6 is 0. Isn't that nice? I think I like this one better than the other one. And yet, they're equivalent equations. So we just made something that looked really ugly into something that's at least possibly doable. What will we hope? That we can factor, especially since this section is on solving a quadratic equation by factoring, okay? What's the only possible factorization for 3z squared? 3z times z. And where do we look next? Sign of the last term. What's that? Minus. What does that tell you about these two signs? Second? Plus and minus. Okay, well, they tell us they're different anyway. What's the only possible factorization for 1? 1 times 1. Let's see if we got it right. Okay, FOIL it. Curses, FOIL again. 3z times z is 3z squared. That part's right. 3z times minus 1 is minus 3z. Z times 1 is plus z. Minus 3z plus z is minus 2z. Right number, but wrong sign. So what do? Change the signs. Change this one to be a minus. Oops. Okay. And make this one a plus. Now let's check it now and see if it works. Z, 3z times z is 3z squared. That's all right. 3z times 1 is 3z. Minus z would be 2z, and then minus 1. Yes, that works. Always check, okay? And then what do we do next? Okay, either 3z minus 1 is equal to 0, or z plus 1, I can't write, is equal to 0. What does the first one, what do you do with that? You know, I thought I brought my watch up here, but I don't see it anywhere. I must have left it. So y'all going to have to tell me when we get low on time. Second? It's what? Okay, add 1 to both sides. Okay, and what does that give us? 3z is equal to 1, divide by 3, and that gives us z is equal to 1/3. We're going to love checking this one, aren't we? Okay, and this one will be? Subtract 1 from both sides, and that gives us z is equal to -1. That'll be a little more fun. But you know what? We really ought to go back to the original equation. Boo hiss, okay? So before we did all of our simplifying, we need to go back to that and plug in these numbers. Oh, no. Okay, what's 1/3 squared? 1/9 divided by 2 would be 1/18. Okay, you know how I think of these things in terms of food? I think of a big pizza here, and it's in 9 slices. I take half of that, I cut each one in 2, I've got 18 slices. So that would be 1/18. You might want to write that down, okay? 1/18, okay? And then 1/3 over 3 would be, divide 1/3 by 3, 1/9. You're absolutely right. You're thinking pieces too, aren't you? I can tell. Okay. Plus 1/9. Okay. Then minus 1/6. I can do that one. Okay. Okay. The question is that equal to 0? Well, what's our least common denominator? Okay, so that would be 1/18 plus, and how many how many 18ths is 9? Yeah, 1/9. That's 2 18ths, right? And then how many 18ths is 1/6? 3 18ths. And is 1 plus 1 minus 3 equal to 0? Yes! Okay, it worked. So yeah, that was a correct answer. All right, let's try the minus 1 in there. What's minus 1 squared? Is what? Positive 1, so that'd be 1/2. And minus 1/3 minus 1/6. Okay? Right? Okay. Least common denominator here. 6. How many 6 is 1/2? 3 6. Minus how many 6 is 1/3? 2 6. And how many 6 is 1/6? It's 1/6. Okay? And is 3 6 minus 1/6 minus 2 6? Yeah, that's 0. All right. Good deal. We love our fractions, don't we? I take it that means we must be time to go. How sad.
Last week I was out because I had surgery. 7 days.
What's that?
The days, will they count against me?
The days.
Like the days that I missed.
Well, you miss the material if you go and pick it up on YouTube and stuff like that.
No, I
It
said
doesn't hurt.
with the passive, like, because I missed 7 days. I know some classes be like, can't miss one.
I grade on how you perform on tests and quizzes.
Okay, so you don't need these.
I don't need them. No.
Okay, that's what I was trying to
Oh, I see. Okay.
Yeah.
Attendance is always
Yes, ma'am. When is the final? Okay, we talked about that earlier. Because I found out last week that some instructors added a section that the rest of us were told we weren't going to teach. The final exam has that section in it. So I'm planning to do a review session for you. It was scheduled for Monday of not next week, but the following week. But I'm planning to do a review session for you to bring you up to speed on that. I'm not going to have those questions count against you, but if you get them right, they get bonus points. So Monday is when it was supposed, not this coming Monday, but the following Monday. That's when it was supposed to be. But we're going to have a review session then if you choose to do it. If you don't want to do it, I'll have someone practice your test for you. But then, so anytime after the review session's over with, either later on Monday or Tuesday or Wednesday or Thursday, anytime you want to come in, you can take the time. Okay. Now we do have a test on Module 13 on this coming Monday. Okay. Did you turn in your quiz? Okay. Good.
Did you